Just to the one. I could do that. I don't want to do it because I start to end up in
No, you are putting it in the
family is just responsibility. Sense all.
Okay, now I can start. Okay. So, after all this work, we have these two lemmas, these two general lemma. The first is tell us a way to create given a family of functions, which are a nice non-negative, locally finite family of functions, f, which assumes several properties. So it's a locally finite. Each of them is smooth on this submanifold with boundary. And we suppose that there is some function beta such that at any point there is so all this happens in Y. Y is not all of S, but it's a submanifold without boundary. So today it will be all S. So later we have to remove from S some critical submanifolds. But now we don't need. So Y, in this lecture Y is all S. And in this lecture, so we suppose that there is a family of functions. This family will be either a displacement function of element with small displacement, or a distance function for some locally finite family of convex sets. And then we found a very general way, assuming there is at any point there is a tangent vector such that the directional derivative of any of the functions which are small at this point, so this sigma xx 3 epsilon denote the finite set of functions which are at most 3 epsilon at x. So this equality holds. So the directional derivative is at least this. Then we have a way to define a continuous flow that increases all these functions. So it starts from the submanifold where with the closure of where all the functions are positive. So all the functions are non-negative, but maybe if there is a distance function from some closed sets, and I don't want to consider the interior of this set. So this is the closure of where the convex all these functions positive, we can deform it to where they're all at least epsilon. So this is, if you want, the epsilon F thick part, and this is the 0 F thick part. So this was, and if this family was gamma invariant for subgroup gamma, this deformation retract will be gamma invariant, it will induce a deformation retract on the Gaussian matrix.
So that you have this, you are in the last point.
Sorry?
In the last hypothesis.
Yes.
Assume that for all x in y there is this.
Yeah,
tangent
for
vector.
x in y there is some tangent, special unit tangent vector.
Then you are taking the dot product with the tangent vector, right? Or is some other vector?
Sorry?
You are taking the dot product of the gradient with the tangent vector, right?
Yeah, this is the direction of a derivative of phi in this direction. The second lemma that we proved yesterday was it's the Adam graded intermediate. It tells us inside the thick submanifold, so M prime will be the thick submanifold this, and now we have and we suppose that its complement is a union of convex sets, a locally finite union, and we suppose that it's homotopic to its epsilon over 2 shrinking, and we suppose that there is some constant B such that, and again a tangent vector like before, such that the directional derivative now for the distance function of this xi is at least this. Under all this assumption, we know how to construct a simplicial complex, a nice small simplicial complex that gives a topology of M. It's homotopic to M prime. So we prove this condition, and now we want to apply them to prove the theorem, and with 2 steps. So what is the theorem that I'm going to prove? So let G be center free semi-simple Lie group. Then there exist 2 constants alpha and b, such that every non-uniform arithmetic S manifold M is homotopic to D alpha volume M simplicial complex. So where S is S of course is symmetric space in one case. So this is the theorem. And the way we do it, we will do the following. First, we will use the first lemma. So this is if you want the picture of the manifold. This will be M. So you know it has cusps. So in higher rank it has 1 cusp, but the cusp doesn't look like that. It looks very difficult to describe. But in rank 1 you have more than, okay, in Q rank 1 you can have several cusps. So first we will show a way how to use the first lemma. We will deform our manifold to M prime. This will be using the first lemma. We will do this, and then we will show that M prime satisfies this condition, and this will prove the theorem. So there are 2 steps. We first need to deform. So we're going to apply this lemma 3.2 with y is all of S, and gamma is the so M is the manifold S mod gamma. Gamma is the fundamental group of M. Oh. So how are we going to do it? So we have so here's the proof. step 1. So let gamma 0 inside gamma be a net subgroup of index k, which is fixed, is an index depending only on g. We prove that there is such a net subgroup. I don't know if last week I denoted it by k, but yesterday it was k. So there is such a subgroup of index k. And net means that every eigenvalue is either 1 or it's not a root of unity. And of every element, and it means that if you have an element which some power of it is unipotent, then it's already. So now let epsilon be epsilon of s over 2, where this is the Margulis form. Okay. So by the way, I will use a bit different epsilon in step 1 and step 2. So I need to tell you what are the functions that I'm using. So let f be all express the function of the form d gamma, where gamma belongs to gamma naught minus identity is unity. So this is the family of function that I'm using. So, and then everything is easy to check. So these functions are defined everywhere. They are positive everywhere. And they're continuous. They are locally finite because gamma is discrete. Everything is easy to verify, except that I need to tell you what is the function beta and what is the direction. Okay, so I will tell you it here, but let me do first a simple lemma. Let C be a regular geodetic So what does it mean? It means that it is contained in a unique flat. So in other words, so in rank 1 every geodesic is regular, but in higher rank, you know, there are geodesic which corresponds to elements like this, which are not, or if you want E to something like this, is not regular, E to minus 2 to lambda is not regular, but okay, but we take a regular geodesic and let G inside G be a parabolic elements fixing G fixing the point at infinity of the geodesic.
So that means the centralizer of the corresponding element is same as the whole torus?
The centralizer is a torus. So it's not an element in G is regular if its centralizer is a torus. So maximal torus. So the centralizer always contain a torus. Always contain a maximal torus. The other element are the elements with minimal centralizer. But there, if you want the elements that's diagonalizable, and if you want that they're adjoint as a minimal repetition of ones. So the kernel of the adjoint is minimal dimension. So So they have the eigenvalue are as much different as possible. And so in rank 1, everything is regular. So in the boundary, you know the boundary of the symmetric space with the Tits metric is a spherical building, and it means that we have a geodesic ends at inside a wild chamber at infinity. If you want. I don't know if you are used to think of Tits metric, but this spherical triangle is inside a sphere at infinity in my picture, and this geodesic is inside the space, but it's terminating in this regular point. That's it. Then for any x in C of t, C of r on this geodesic, so x is some point. So geodesic usually draw like this, right? So this is c of t, and we have x here. So every x here, the gradient of the displacement function x is non-zero. That's what that's the lemma. And the proof is very simple. It's one line. So let me write the proof. So proof is as follows. So suppose by way of contradiction that so in fact I need more. I need to say that let's suppose that this is C of minus, so C goes in this direction. So I need t to the t of the gamma of C of t equal. So suppose, okay, so t goes to d by gamma in g. Yeah? So to dg of C of t is a convex function. Which is non-decreasing, which is non-decreasing. Which is non-decreasing. If this d to the t of C of t is 0 for some t and some t, then it is 0 for some t0, let's say t0, then d to the t of dg of ct dg of ct is 0 in all the past for every t which is smaller than t0, right? Because it's a convex non-decreasing function, and by analyticity and by analyticity, I don't know how many spelling mistakes here, but you understand. It is constantly 0. dg of ct equals 0 for every t. But then it implies that g takes this geodesic to a parallel geodesic. This implies that g of c is parallel to c. But what does it mean? If it's parallel to c, it means that g must preserve G preserves the maximal flat determined by C. C is contained in a unique maximal flat, and G takes it to itself. Okay, but now you know, so G induces an isometry of this flat. But what is this flat? This flat is isometric to Rn. To R, if n is the rank, this flat is isometric to the maximal flat, let's call it F. F is isometric to Rn, where n is the rank of the space. And any isometry of Rn, it is semi-simple. It has a minimal displacement somewhere. Any isometry of Rn attains its minimal displacement somewhere. So, and we know that if an isometry preserves some convex sets, then its minimal displacement is attained in this set. So if it's every displacement, if you have displacement somewhere, you project it to this convex set, the displacement can only decrease. So this implies that G is semi-simple. A contradiction. Every isometry which preserves a flat is semi-simple. It attains its minimal displacement. Okay, so the lemma is proved. Now I'm going to define beta. The function beta and the constant C I will define in a minute. And the constant, the direction n. So let U inside G be a maximal unipotent subgroup. Let W inside the boundary of the symmetric space inside it be the fixed Weil chamber corresponding to U. Be the Weil chamber corresponding so every unipotent subgroup, there is a unique Weil chamber. Every maximal, there is a unique Weil chamber, which is exactly the set of all fixed points on this subgroup. So if from the classical theory of symmetric space, and I need to define a point. Let P in W infinity be the center of mass. The center of mass. So what do I mean? So this W is isometric to a spherical simplex, and the spherical simplex is contained in a half sphere. It's always the case for Weil chamber. It's contained in a half sphere and it has non-empty interior. So if you want, P is defined as the integral over the integral over W dW over its norm, where I identify W integral over W, where I identify this simplex as a simplex in the Euclidean sphere. Okay, so it's just the center of mass of this. So you can, it is well defined. It is because it is contained in a half sphere. This is well defined. So in the book of Baumann, Gromov, Schroeder, they discuss very detailed it's metric at infinity and the Weyl chamber, and I think they also define the center of mass, but anyhow, it's well defined. So it's the center of the Weyl chamber. And now I define what is the theorem of pooling, but I can state it several times, so I delete it. And now I define that beta of t, I need to define a function, b let first C of C from R to C to S be the regular geodesic with for every x. Let's see with the geodesic with C at 0 equals x and C at minus infinity equals p, center of mass. Okay? So for every x, there is such a geodesic, and define beta of t to be the minimum of the d to dt at t equals 0 of c of d g of c of t of cxt, where x is a point in the symmetric space and g is an element in U such that the displacement fx is exactly t. This is better. And I need to tell you why this is well defined. I mean, I take the minimum of something. This something is always positive. This is the lemma before. But the minimum is taken over a huge set. X can be everywhere. But we know that the parabolic subgroup, which normalizes U, acts transitively on the symmetric space. So I can move X to a fixed point. So this is actually the same as the minimum of sensing dg, and now it's a fixed point that I fix my favorite point in the symmetric space, and g in U such as d g x of this fixed point is right, and this I can do because I can move, because the action is transitive, I can move x to x naught by an element which preserves U. So there is an element that preserves this Weyl chamber at infinity. It belongs to the parabolic subgroup normalized in U and take x to x naught. And this is the compact set. Compact. And this function, the function that is given here, so t is fixed. T is fixed. For fixed t, I have a function which, from this compact set, to 2r plus. So for each element, it gives me the derivative of the displacement function, the directional derivative, this direction. What is written here is the directional derivative of dg at x naught times c dot. And the function that sends g to this is a continuous, it's an analytic function. So displacement function is something you can write a formula for every symmetric space. I didn't do it, but every symmetric space you can embed inside the symmetric space of SLN in the totally geodesic sub. You can embed G, every semi-simple group as a transpose invariant inside the symmetric space, and there you can actually compute. You can compute displacement function. You can write formula. You can differentiate, and you see that everything is analytical. Maybe I should do it tomorrow. Just spend 10 minutes to show you how to do it. But this function is analytic, so it's a continuous function. So on this compact set, you get a minimum, positive minimum. This is how I define beta. So beta is defined in this way. And what is nx? Nx is, okay, I need to explain. So beta I define. So, and this is why I made this remark that this beta is defined for every positive t. But I remarked here that since all the functions, the displacement of unipotent are never zero, I don't need to define beta at zero. Okay. And so beta is defined, and now I need to tell you what is nx. So I think we'll finish step one. And if you know what it is. So given x inside S, let sigma x I need 3 epsilon. Okay. So in the beginning of the proof, forgive me, in the beginning of the proof I wrote that I take epsilon to be 1/2 of modulus lemma, but I meant 1/3 of modulus lemma. So I needed 3 epsilon still satisfies the modulus lemma. So remember, these are all the functions gamma in my net, which are not identical. Okay, I don't mind, take the identity actually. All the functions in my net, such that, I don't want to do that. Such that the displacement of gamma at x is at most 3 epsilon. So this is a finite set. So by the arithmetic version of the modulus lemma, variant of modulus lemma, sigma x 3 epsilon is contained in, let's call it u x 3 epsilon. This is a connected unipotent group, and I can take it maximal. Maximal connected unipotent subgroup of. Okay. There is some choice here. This group may be containing many, but I don't care. I take one of them. Let P be, let W of this U x3 epsilon be the wild chamber infinity, corresponding y terminal at infinity, infinity and P its center. And C x be the geodesic with Cx at 0 equals x and Cx minus infinity equals p. And now I define nx hat to be c dot x is finished. Because now I define the direction at any point, and by definition we have what we want, and we have finished the proof of step 1. Finish the proof of step 1. Any questions? So, okay, step 2. Step 2 is very similar, and we have all the ingredients, so we just need to do some small checking. Verify some small thing, but let's first, okay, step 2. Let m prime be f greater equal than epsilon, where f is given in step 1 is all this d gamma such that gamma is in gamma minus identity uniform. And gamma not minus identity. Now okay. If gamma belongs to gamma, not to the net, minus identity, or even with identity, then gamma to the power I belongs to gamma naught for some I less than equals k. Okay. So d gamma to the power I at the point x is at most I times g gamma at the same point. Hence, okay. This is just a mark. Now, if x belongs to m prime tilde, so in the universe, it's in the universal kernel, and gamma and gamma is in gamma minus identity, such that d gamma of x, suppose it's really simple. But let me do this. Okay. We already know, okay, if x is in M prime, then for any gamma, which for any, let's not call it gamma, but alpha, which is in gamma naught minus identity, we have d gamma, d alpha of x is at least epsilon. Right? We know that. Because this is how the epsilon thick power is. Yeah. Although we use only unipotent, but we know that all the elements have small displacement. If it's a net, it consists of unipotent. So this we know. Then alpha. Thus, for every gamma in gamma, d minus identity, d gamma of x is at least epsilon over k. Right? Because otherwise, take this small power of gamma, which is in gamma naught, and you get the conclusion. Okay. So this implies that M prime is inside M greater or equal than epsilon over k. Okay. So epsilon over k is probably what we need to. We now check. We check that the condition of the second lemma of lemma called for one holds with let's say epsilon 0 equal epsilon over k. So here, suppose here everything was epsilon 0. And, I don't want to start. Okay, maybe it's not so much changes. So everything you see here epsilon, I just don't want it to be the same epsilon as before. Yeah. Okay. Sound good. Okay. So we check that. Now, I need to tell you, and now it's clear, right? It's clear that M prime is given, is submanifold with boundary, and the complement of it, which we can call X, is a locally finite union of a convex set with smooth boundary, and we know what are the convex sets are sublevel sets of this unipotent from the net, and everything is satisfied. Everything is satisfied, and all we need to check is okay. I need to tell you why M prime is homotopic to its shrinking, and what are the directions. So we need to show everything is easy to verify. So clearly, M prime is of the form so that x, which is M minus M prime, satisfies that x tilde is a union of d gamma less than epsilon, gamma inside gamma naught minus identity. So it's a locally finite union of convex and its smooth. Now, so I need to answer why M prime is homotopic to M prime epsilon shrinking, and why, and what are the direction, and blah, blah. So I will tell you. I will again why this. Again, we use this deformation reflex. Again. we use the deformation retract lemma 3.2. With respect to which function? With respect to the displacement function, with respect to f is now the family of distance function from the sets d gamma less than epsilon. These are these functions. And everything is easy to check. It's a locally finite, again, because of the discreteness. It's a non-negative function, which are smooth on where they're positive, on the closure of where they're positive, and everything is satisfied. I need to tell you.
What's the notation?
Sorry?
F equals this. What is the capital D? What is the notation?
So now I'm going to use lemma 3.2.
That is overrated. Okay?
That's a function. And again, okay, I need to tell. So let's write more precise. Yes. So f is what? Let's write precisely. So f is the function, a distance function from the sets d gamma less than or equal epsilon, where gamma belongs to gamma naught minus identity is uniform. And it's locally finite. I only need to tell you what is the direction and what is the function beta. And okay.
Epsilon not everywhere.
Yeah, epsilon. No, here is still the same epsilon because it's a decent. I need.
You need to deformation retract it to that, right?
No, I'm using this. It's the same epsilon that define x tilde. I need to get
further.
Yeah, further from this set. But I need to tell you what is the direction. So, so I need to tell you what is beta. So we're going to use. We'll use the same nx as before. We have the direction because if I'm close to where the displacement function is less than epsilon, then the displacement function is still small, so it's still connected. The only important that can still use the same direction, and we use the beta will be a constant function, which let's call it beta naught. Will be the constant function, which is the beta from before at the value epsilon. Beta from before. And the fact that we will have this condition, the fact that gradient of this distance function from g gamma less than epsilon at x times nx is bigger than beta follows from convexity of this distance function. This is a convex set, so the distance from it is a convex function. So we know that in some point in the past we had it. Like if exactly we compute it on the boundary, then it's follow from step 1. And now, okay. This is actually not so good. There's something to check. We need to check. It's proven as follows. Okay, and once I prove this will already finish. Then I will use the same. Actually, I will call it beta, but it will also be 1 over b. 1 over b, where b is the constant that we will need in a minute for lemma program. And this is a computation. It's actually a nice computation. So I will write it. Let's do the computation. Okay. So we are doing the following. Let x in S such that the distance from d gamma less than epsilon of x is less than epsilon naught, where gamma is in gamma naught minus identity unipotent. Let Cx be the geodesic as before. So, Cx at 0 is x, and Cx at minus infinity is the point which is the center of this function. And we know we defined nx, let's say, nx, we define it as cx dot. And now I have the following computation to do. So I'll do it here. And we are very close to the end of the course, but we need to do this computation. Okay, we need to compute nx inner product with a gradient of the distance function from d gamma less than epsilon x. So this is equal to d t at t equals 0 of d gamma of the distance to d gamma less than epsilon at the geodesic field. That's the direction. Now, this is greater than equal because this function is convex to dt of the same, we do exactly the same expression, but when I compute it at some point in the past, where t0 is less than 0, and what will be t0? T0, I'll choose it to be the time that the displacement of gamma is exactly 0. So I choose it to be exactly the time that this is I'm in the boundary of this set. So we assume that d gamma of C at T0 equals epsilon. So now it's bigger than epsilon, and in the past, at some point, it was epsilon. So this is how I choose the... Okay, great. So this is exactly the normal vector to this set. Okay, so this is equal to n to c dot cx. Okay, it's the same x, yeah, cx dot at the time t0 cross what is the normal to this? It's exactly the gradient of d gamma normalized by x squared. But when at the same point, at the same, let's call this point, let's call this point x naught. Yes, I assume that this is x naught, and this x naught is c of t. Okay, so this is exactly the same. And now, I'm using a function that the gradient, distance function, displacement function is 2 Lifshitz. So this norm is at most 2. So this is at least Cx dot T naught 1/2 gradient d gamma x naught. And now we see, so this is exactly 1/2 d to dt at t equals t naught of the displacement function now of Cx of this is exactly 1/2 beta of okay, by definition this is okay. Now I would like a picture. Merely is computation. I like this okay, great. and this finished the proof.
We should have also a group picture. We should also have a group picture.
So I actually proved this. I proved this, but I'm going to use the same beta, the same. So this finished the proof of everything actually. So it finished the proof that we can use lemma 3.2 for this, but we already have this b and this n, and we've just verified that it satisfies, so we also have this condition. So this finished the proof of step 2, and we're done. Okay. Okay, that's it. And now I have half an hour, right?
Yeah.
And okay, so I thought that this would take me half an hour, but okay, but still half an hour is good. I want to describe now the case of the rank 1. The rank 1 case is very easy to feel, like you can really see the picture. So, in a sense, we're not.
But this also works for rank 1, right? What you did.
Yeah, this theorem is in general also non-uniform, but in rank 1, now I'm going to prove the other theorem for. Okay. So what is the theorem that I'm assuming now? So the next half an hour I will speak about rank 1, and actually I will need an hour. So I will start to speak about rank 1, and I will continue tomorrow a bit about rank 1. So actually now I will tell you, okay, I will start to discuss rank 1. I don't want to do it too fast. And then I will continue tomorrow about rank 1. I also will discuss the 3-dimensional case, which is, we get a bit weaker result, because proof. So now we're going to prove the rank one case. And we will not, of course we will need lemma for 1. Lemma for 1 is crucial all the time. But we will not need lemma 3.2. Instead we use star construction. So we could use lemma 3.2, but it's much simpler to use the star construction. So the rank 1 case. So basically, I want to prove the following. So let S so theorem. So let S be a rank 1 symmetric space. So there exist D and alpha such that any S manifold, not just arithmetic, non-uniform, is such that for any S manifold, the fundamental group of M is isomorphic to the fundamental group of R for some D alpha volume M simplicial complex R. But now for this I need to assume such that if the dimension of S is not 3. And it's the same as saying that every torsion-free lattice G is the fundamental group of some D alpha simplicial complex. But this simplicial complex it will not be necessarily aspherical. If it was aspherical, then it would be homotopic to it. But in general, it is not aspherical. If
here you have both compact and non-compact.
Yeah, it's both compact and non-compact. If D equals 3, this is not true. Pi 1 of M is a quotient of pi 1 of R for some D alpha simplicial. Okay, that's not so big deal to be a quotient of just tell you something about the number generator, but we know more about this quotient.
The alpha times volume in the game.
R.
Sorry?
What is R?
For some
That is right.
different complex.
Right. And below, what are the quotient of D alpha simplicial complex and D alpha times volume M?
D alpha volume M. Oh, I don't like to say that. Let's forget it. Let me write the second theorem that I will prove, which will actually follow from this. So if beam S is not 3, any torsion-free lattice admits a presentation gamma can be written as a generating set and relations with both generating set size and relation size at most constant times volume of G mod gamma, and every R the length of every relation is at most 3 for every R in R. So this is a straightforward consequence of the previous theorem, because for every such a crystal complex you can build such a presentation. But the reason I wrote it separately is because I wanted to write a corollary for dimension 3.
What is less than equal to 3?
Sorry?
What is less than equal to 3?
The length of R. Every relation, if you write it, it's a product of generator. For if it's still a theorem, dim S equals 3, so we just say that S is the Boolean space of dimension 3. So S is H3. Then gamma is isomorphic to sigma R, where sigma and R are both bounded by this. So I cannot say that the length of the relation is short.
And C depends on S only.
Yeah. C depends on it. And here we cannot say, and it's not true that, but we will know, we will see more. We will see in the proof, we will see what are the relations that we don't know the length. We will see where they come from. Okay, so I will start to explain this theorem by telling you the thick-thin decomposition, which I already wrote once, but I didn't explain. Now I want to explain. I want to elaborate a bit about the thick-thin decomposition. This is the theorem of Stilson. And it tells you, so let S be rank 1 symmetric space. And epsilon, the Margulis constant. So then M less than epsilon admits sorry. Of course, let M be a finite volume S manifold. Then the thick part, or the thin part, admits at most C times volume M, and this is some constant. It's not the same constant as before. It's some constant. When I write C, I mean a constant, but in every theorem, C is a different constant. C times volume M. Maybe I should write constant. So constant times volume M, a connected component. Connected component which can be which could be of two types, two types. So there are only two types of connected components. So the first is a tubular neighborhood of a short closed geodesic. And this is homeomorphic to a ball of dimension d s minus 1 bundle over a circle. And the second type is a cusp. Okay, I have enough time to read. Second type is a cusp. And this is homeomorphic to a n cross r, where n is a compact, again, in s minus 1 and 4. And it's, if S was hyperbolic, it would be a crystallographic manifold event, like a Euclidean. And if dim S is bigger than 2, M greater than equal, epsilon is connected. And actually, by our theorem, lemma 4 1, blah blah blah, we can actually say that this is connected and homotopically equivalent to simplicial process. Okay, so the picture again is the following. Yes, this will be a cusp, and this will be a tube. Tubular neighborhood of this. This is the short geodesic. And okay, you see, in this case, the thick part is not. This is the thick part. This and also this. And in this case, it's not connected, but it's in dimension 2. So why this theorem is true? So first let me explain the last line. Why it is connected if the dimension is bigger than 2? Because we know what are the connected components. The connected component, the boundary of this connected component is connected. And the boundary of this connected component, this is a ball bundle over a circle. So we see here, the ball is of dimension 1, so it's a segment times a circle. It's a segment bundle over a circle. It doesn't have to be product, it could be a magistrate, it could be non-orientable. But it's a ball bundle over the circle, and the boundary of it is a sphere bundle over the circle. But the sphere bundle, so in dimension 2, the sphere has dimension 1, so it's 2 points, it's not connected. But in other dimension, the sphere is also connected. So if the boundary of each component is connected, then the complement is connected. Because if you have 2 points in the complement, if you have 2 points in the thick part, you can draw a line between them. If the line passes through some component, stay on its boundary. The boundary is connected, you can, if you go in and out, you can just go around. So this shows why the thick part is connected. So the thick part connected follows from the type of the component, but also why the number of components is bounded. The number of components is bounded because I'm wave-handing instead of writing it because of shortage of time, but at the boundary of each component, you can find an injected ball of radius epsilon over 2 or epsilon over 3, right? So at the boundary of each component, you can find an injected ball. The injected radius is not small anymore, and these balls will be disjoint when you see the proof. So it means that each component, connected component, contributes some definite amount to the volume, so the number of components is bounded linearly by the volume. So these poles are the reason that the number of components is bounded linearly by the volume. Okay. So, and this will be, we will need this bound when we prove that three-dimensional version of the theorem. We will add one relation for each connected component, and we need to know that the number of components is bounded by the volume. Okay, so how the theorem, so let me prove the theorem. So let m less than epsilon let this be a connected component of the universal kernel of the thin part. And let gamma naught inside gamma be the elements. Gamma naught is all gamma in gamma, such that gamma takes this component to itself. So you know this kind of sets is called gamma precisely invariant. Every translation of them is either the same or disjoint. So if you want this in the manifold, the corresponding this is a fundamental group if you want to, not exactly because the boundary, but yeah. So I will claim that gamma naught in the tube case, in the tube case will be infinite cyclic, and in the cusp case it will consist of unipotent elements which preserve a Hall sphere. So by the Margulis lemma, even the weaker version of Margulis lemma, gamma naught is virtually nilpotent. So let n be nilpotent of finite index, and let if you want n in n, or let's call it alpha, be a central element, a non-trivial central element. And in important group will be the non-trivial center, so we can find it, we can take this. Okay. So there are two cases. Either alpha is hyperbolic or it's parabolic. Actually, in rank 1, the parabolics are unipotent, but I don't really need it. But either alpha is hyperbolic or it's unipotent. If okay, now for any gamma in this gamma naught, gamma to some power belongs to n. Hence, commute with alpha. Now, the property, in rank 1, if two isometry commute, if you commute with hyperbolic elements, okay, suppose I'm not considering now elliptic isometry, just hyperbolic and unipotent. So if hyperbolic and unipotent cannot commute. So this is an exercise. But an easy exercise, because if you commute with hyperbolic, you must preserve its axis. If it preserves its axis, you move it somewhere, so you also have this as an exercise. So hyperbolic and unipotent do not commute. Okay, so suppose that this alpha is hyperbolic, then gamma to the n commute with it, so it's also hyperbolic. But gamma commutes with gamma to the n, so gamma is hyperbolic. And not just moreover, if two hyperbolic commute, they have the same axis. They share a common axis. Common axis. If two unipotent commute, they have the same fixed point in infinity. If two unipotent commute, they have the same fixed point at infinity. Okay, so this tells you that all the elements in gamma naught are either hyperbolic with the same axis as alpha, or they are all unipotent with the same fixed point at infinity. This implies if alpha is hyperbolic, then all gamma naught consists of hyperbolic sharing a common axis. And okay, so we have a discrete group of translation of the same axis. Take the element with minimal translation. There must be one with minimal translation, and it must generate this group. The one with minimal translation with minimal translation generate gamma in the hyperbolic case. And gamma naught is 3. So it's not just contain a normal subgroup of finite index which is nilpotent, it is cyclic. You don't need to go to finite index and you don't need nilpotent and abelian. And in that case, so look what happens. So I'm in the hyperbolic case. You have some geodesic, and gamma naught translates gamma naught. The one with minimal translation, let's call it gamma naught, and you have gamma naught in the cyclic group generated by gamma. So it translates and it's also rotate around. So you look where, so you know that this m less than or equal epsilon, the connected component, will be consist of all the thing of the following, d gamma naught to some power I less than epsilon. It will be the union of this. And I have to look at gamma naught and gamma naught square and finitely many powers, because at some point the displacement will be more than epsilon, and I don't need to consider. So I only need to consider finitely many powers, and each of them has rotation. So for each of them, I have a neighborhood of this geodesic where the displacement is less than epsilon. It could be, by the way, that the neighborhood of gamma square, so you think that the biggest neighborhood is the one of gamma, because gamma is the minimal displacement here, so here you can go more in the vertical edge. But maybe gamma rotates by pi degree. And gamma square doesn't rotate at all. And so it could be a priori that gamma square is bigger neighborhood. Could be. But it's a finite union of convex sets which are around this geodesic. And if you look, okay, so I'm not going to describe. Let me spend one more minute about this. So this is the picture, the topological picture. If you cut it vertically, so what does it mean cut it vertically? So at least in the hyperbolic case, it's very convenient. We can use the fact that the vertical whole spheres. We know, at least I like, for this kind of argument, I like to consider the upper half plane model, upper half space model. And in the upper half space model, if you consider the upper half space model, so it's funny that we draw this thing and think that there is a upper half space, but okay, so I don't know, there is this upper half space model, and you have this point at infinity, and suppose that this is the geodesic on which you translate and rotate around. So the neighborhood looks something like this, but you can cut it with this Euclidean whole sphere, which at a given altitude. And then if you look at the Euclidean whole sphere, the cut will be, so in the Euclidean whole sphere, when d gamma naught less than epsilon, so this is I cut it with this whole sphere, it should look like something like this, and maybe d gamma square less than epsilon looks like something like this. And maybe d gamma cube less than epsilon will be something like this. But you can actually show that there are only finitely many coaxial, in a hyperbolic case, finitely many coaxial ellipsoids. They could be very, very thin, some of them. That's why, but they're all coaxial. And actually, in the three-dimensional case, it doesn't happen. In the three-dimensional case, you translate, and you have only 2 dimensions left, so you can rotate. You can rotate by less, you can rotate by more, but you can only rotate. You cannot do something more complicated. So the cut will always be a ball, not an ellipsoid, but a real ball. So in the three-dimensional case, this is not the picture. The picture is much nicer. It's actually smooth. But in 4 dimensions, it's already complicated. And so that's why the thin part is, the boundary is not smooth. You have these corners. But you see the corner, this is a hint for tomorrow lecture, the angles at the corner are at least pi/2. Here we can compute, we can do explicit computation in hyperbolic geometry and show you that these are ellipsoid with coaxial ellipsoid, and the angle are at least pi/2. We will show that the same world in every symmetric place. So this will be the highlight of tomorrow's lecture. But this gives you some description of what the thin part looks like. I like very much the reference for this in the Thurston book, Three-Dimensional Geometry and Topology. And but if you really want to see this, to understand more, a very good reference for this is the book by Beneditti and Petroni on the lecture on polygeometry. So for this specific thing, it's very good reference. So I didn't say much about the unipotent case, but again, it's the same. If gamma naught is unipotent, then all the group is unipotent, it preserves the whole sphere, and it masses compactly, and you get this structure. It preserves the whole ball, and it's easy to see. That's it. Okay, so tomorrow, I will start by using the fixed in decomposition to show you a very fast proof using lemma 4.1 and fixed in decomposition of the hyperbolic case and this theorem. And then I will discuss the compact higher rank case. Because in higher rank, everything is arithmetic. So if it's either non-compact, which we already did, or it's compact. And so we can assume that we're in the compact case. And in higher rank after we do the rank 1 case. And then this I hope to finish at the first lecture. So in the second lecture I want to give you to do something else, which is invariant random subgroup, which I call a modern technique to attack the space of lattices in Lie group. And then I will show you a theorem about the Betty numbers, which is stronger than what we can. Okay, it doesn't apply the theorem about homotopy type, but it's stronger than the corollaries about Betty numbers that we can deduce from the theorems about homotopy type that I described. But it also indicates that the results about homotopy type cannot be improved. That the growth of homotopy type is really linear. We'll see that the growth of Betty number are usually sublinear, but we'll also show that some Betty numbers go linear. So okay, this is hopefully 3 hours would be enough for that. But, okay.
Tomorrow 2 lectures.
Tomorrow 2 lectures. One is
11 o'clock.
11,
12:30 and
yeah.
2:30.
At 11, yeah. And then okay.